Okay, on to part 2 for the velocity and acceleration information. So when we ended the last half of the video, we had calculated for the ball rolling on a horizontal surface its average velocity. And we found the average velocity for a line of best fits. Wasn't the best, but it was pretty good. And we calculated in centimeters per second, and we calculated what it was in meters per second, a more standard unit as well. So what if instead of having something moving on a flat surface that it already got going before the video started, what if we watched it start from rest, meaning zero velocity, and it rolls down an incline? It's going to go from not moving to being in motion. That implies that there's a change in velocity. So we want to see what the graph of that might look like. Is it going to be a straight line? Is it going to be a steeper straight line? Is it going to, like, what's it going to look like? You can take a moment to consider that and think, well, if we got a line that's got a certain steepness and that represents a particular velocity, what if the velocity is changing? How should the graph look? But first, let's go ahead and define that term acceleration. So scroll down here to the definitions that we had. We said that average speed and average velocity are very similar, speed being the total distance divided by time interval, and average velocity being the displacement divided by a time interval. Now we've got average acceleration, which is defined as the change in velocity for a time interval. So if something starts off at one particular velocity, one quickness, and then it transitions to a new velocity, there's a change in velocity that goes by. We can subtract the two, and we can divide it by however long it took for that to happen. That's defined as average acceleration. We will ultimately have different values for both velocity and acceleration called instantaneous, but for right now, we're looking at average. So we're going to introduce an equation for that. Average acceleration will be A for acceleration with a bar over it to represent the average or mean value, and it will now be delta V divided by delta t. Now, we're going to have a hard time calculating average velocity changes for the data we're going to have, but we want to at least see what's going on, because what's very important to note here is that velocity is a rate of change. I'm going to highlight the delta x there. It's the rate that position changes. Acceleration is a rate of change as well. It's the rate that velocity changes, which means this is sort of like a rate of change of a rate of change with respect to time. And this is when calculus is going to start coming in handy. We can't really do this. Double deltas like that, that just doesn't look right. So at some point we're going to get into calculus, and that'll allow us to figure what the acceleration is directly from position. But right now it's important to note that acceleration is the rate that velocity changes, but velocity is the rate that position changes. So we're kind of doing a double rate of change here. Now, let's go ahead and take a look at the video and see what does the acceleration look like. We'll watch it again here. And like the previous video we've done, I started off with the timer already going. So we'll have to do a little subtraction of time there, find out what the time interval is. But you can see it moving. And to me, it looks like it's noticeably going faster at the end of the video. So we want to be able to calculate some information, maybe average velocity over the whole trip, maybe average velocity for different little segments of the trip. But starting, we want to get some actual numbers together. So I'm going to go back here. Let's see, when does my hand stop touching the ball? Right about there. It looks like my hand stopped touching. So 4.9 seconds is going to be what we have to take away from our information for time. And since we got the ruler set up here, let's go ahead and say we're going to go every 10 centimeters or every 0.1 meters. Let's go ahead and fill in our table with that position information. So we're going to start at 0, and we're going to go to 0.1 meters, 0.2 meters, 0.3, 0.4, and oopsie, I didn't make my table big enough, 0.5. And it says centimeters, so let's change it to meters. Remember, there's 100, sorry, I'm adjusting my chair there. There's 100 centimeters for every meter. So let's go ahead and see if we can get some times collected for those. We've got at time, position 0. We want that to be time 0. We don't want to actually put in 4.9 seconds. So that means everything we measure, and then we're going to subtract 4.9 seconds from it. Now that's going to be a standard thing. I'm not going to bore you with the details of subtracting on a calculator screen every one of those, but let's go ahead and see what we get here. So if I scroll the video till it looks like the ball is as close to 10 centimeters with perspective involved, looks like 5.52, which would give us 0.62 seconds. And let's go ahead and do it for all of the others there. I'm just going to kind of rattle off what they are, and then we can do the subtraction afterwards. So if you scroll from here, about right there, 5.77. Then if we go to 30 centimeters, looks like we're about 5.98. You already see that the time interval is decreasing, which for the same displacement, less time, that's what we saw in the previous video. Then we go to about 40. Again, I'm kind of looking at perspective here. We're getting 6.13. And then for 50 centimeters, somewhere around there, maybe, looks like perspective-wise. So 6.3. Okay, let's go ahead and fill in our timetable with that information. So I got times here. I'm going to subtract 4.9 from all of them. So doing a subtraction of 4.9 from all those, we get these, not exactly pretty numbers, are they? But we can still try our best to graph these. We're not going to do perfection, but we're going to go ahead and look at time 0, position 0, all the way up to time 1.4, position 0.5. So how about you go ahead and get this data down and start graphing, and then hit the pause button, and then we'll go ahead and take a look at all of the data together. And in full disclosure, before I get everything graphed there, I realize I'm acting like a total sucker here, and I forgot that I can add backgrounds of graph paper. I mean, geez, come on, use technology. Okay, anyways, now that I got that all set up, we'll go ahead and graph some data points there. Now, I've got my data points plotted here, and you can see there's a very large time gap to get to 0.1 meters, smaller time gap to get to 0.2, and then, you know, they seem like they're getting a little shorter. The little delta t's here are, you know, they're getting smaller, but it's starting to almost look kind of linear here, but it's not quite linear. We can't just draw a straight line in there. In fact, if we go ahead and try to draw a straight line in there, if I go and draw one in green, let's say, a straight line that kind of goes through those 3 data points does not go through the other. And if I try to include that one, I'm excluding the others, and so on and so on. It's kind of difficult to, you know, you can't just cut one line through all the data points. So what we should do here, just to kind of get an idea, is connect the dots kind of one by one. So I'll do the kind of with dotted lines here, which makes it really hard to delete things later, but we can definitely see that the slope of this line is not constant. It starts to look kind of constant at the end, but that might just be because we're at a weird angle. But we saw up above that an object that was moving at a particular speed, if it were to go faster, would have a steeper slope, and if it was to go slower, it would have a lower slope. Well, here, if we have an object that is starting off from rest, it should start off slow, which means it'll have a very low average velocity. And then as it So we'll go slow/low slope. Gotta put all the letters in there. Zook, come on. But as it goes faster and faster, as it goes down the incline, it accelerates. It starts gaining velocity as time goes by. It essentially speeds up to the point where it has a fast or high velocity, which will be a steep slope. Now we can calculate basically a little delta t and delta x's here to calculate the velocity of this slope, that slope, and the others. And then we can compare them and see that the velocity values do go up. But what's really important here is to note that from this graph, even without the numbers, if we just had this sort of parabolic curve, we could immediately know that the object was getting faster and not slowing down. If we had a graph that looked somewhat different, I don't know, like something that went like this, then it would be an object that started out fast because it has a very, very steep slope, and then it would be moving very slow as we approach that further time. Now, eventually, if it flattened out, that would be zero velocity because there's no slope. But what's really important here is to note that you can determine some things about the object's motion without even knowing the numbers. So we're going to go ahead and stop this video here, and next video we will be starting to take a look at a little bit more details about calculation of acceleration, but that's where we're going to stop here. Thanks for watching.